Hello, and welcome to another book club episode. Today, we're going to be continuing where we left off. We were doing exercises. So, let's see if we can finish that up. So, let me see here. So I believe we left off doing 1.9. We did 1 through 8, right? Let me just double check that. If YouTube will refresh. Well, YouTube isn't refreshing. I clearly have internet. I'm not dropping any frames, but YouTube does not want to cooperate today. And I accidentally opened a new window. So what is loading in this tab now? So is anything gonna load for me here? I mean, I'm streaming, I'm not dropping any frames according to OBS. But apparently my download is dead. I can't... I've only got a one-way connection here, guys. So yeah, nothing's loading for me right now. I mean, we don't really need internet to do a book club episode though. I hope the stream is okay though. Let me check on my phone. Okay, let me see here. Twitch. Do I have Twitch on here? I know I've got it somewhere. There it is. Okay, now can I see my own channel? It says I'm live. Okay, now can I see my own channel? It says I'm live. So yeah, it seems to be streaming fine. So we're just gonna roll with it, I guess. Okay, so since I can't load any web pages, I can't check what I did last time. So let me just reread these. 1.8 was yeah, that was the one we did last. That was the the one about power with the Pentium 4 Prescott and the Core i5 Ivy bridge. So I guess we're going on to 1.9. Assume for arithmetic load, store, and branch instructions, a processor has CPIs of 1, 12, and 5 respectively. Also assume that on a single processor, a program requires the execution of 2.56 times 10 to the 9th arithmetic instructions, 1.28 times 10 to the 9th load store instructions, and 256 million branch instructions. Assume that each processor has a 2 gigahertz clock frequency. Okay, so I guess we should start by writing those out in Milton. So let's just go down here since we're near the equations that we use. I'll go right here. Okay. So we have 2.56 times 10 to the 9th (1.28) times 10 to the 9th, and 256 million. Okay, first of all, so let's get the zeros in here. So let me see here. This would be 256,000, right? So that would be 2,025,256 million. Right? And then if we do the zeros here, 1, 2, 8, and then 1, 2, 3, 4, 5, 6, 7, I think. So that moves the decimal place 1, 2, 3, 4, 5, 6, 7, 8, 9 places. And then this one is 2, 5, 6, and the same amount of zeros, right? So I think we have numbers like that. So if we want to do the good old fudging, so like if I take this number here and move the decimal place like 7 places, like this one would be 25.6, this one would be 256, and this one would be 128. But I mean, I already counted the zeros, so like we should probably, instead of doing that, I mean, I suppose like this one would be 0.256 if you just did 2.56, 1.28, and this would be 0.256. But like I say, we already counted the decimals, so we should probably just use the proper numbers, right? So let me see here. And both processors are 2 gigahertz. Or wait, both processors. I thought this was a single processor. It says assume that each processor has a 2 gigahertz clock frequency. But before that, we were talking about a single processor. It says assume blah blah blah. A processor has also assume that on a single processor. But then here it says assume that each processor. I think that's just a mistake in the wording. So let's just say 2 gigahertz. Assume that as the program is parallelized to run over multiple cores, the number of arithmetic and load store instructions per processor is divided by 0.7 times p, where p is the number of processors. So the number of arithmetic and load store instructions is going to be divided by 0.7 times number of processors, but the number of branch instructions per processor remains the same. So find the total execution time for this program on 1, 2, 4, and 8 processors, and show the relative speedup of the 2, 4, and 8 processors result relative to the single processor result. Okay, so I see why they said each processor here. We're talking about multiple processors as in multiple cores. So we're talking about parallelizing across cores. And so when they say the number of branch instructions per processor remains the same, do they mean that each processor will be doing 256 million branch instructions? Or do they mean that it'll be split up across the cores? So 256 divided by p. If you read it literally, the number of branch instructions per processor remains the same, then I think that would be 256 million branch instructions per processor. Right, and then for the arithmetic and load store operations, it's 0.7 times p, like divided by 0.7 times p, because like just if you split the workload up across cores, it would be divided by p, but you're not going to get perfect like efficiency. It's not going to be literally the same as like splitting it up, dividing by p. Like that's not perfect. So they're saying it's only 0.7 times p is the efficiency there, I guess, of the parallelization. So find the total execution time. So first of all, let's just do on a single core, because they say we need to find it on 1, 2, 4, and 8. So So those are the ones we need to find time for. So for one processor, let's go back to our CPU time equation. So CPU time is equal to instruction count times CPI divided by clock rate, and we know all three of those values. So if we say instructions, it was instructions times CPI divided by clock rate, right? Yeah, instructions times CPI divided by clock rate. So that's going to be 2.56 times 10 to the 9th. That number times CPI of 1. And then we need to sum it with the CPI and instructions of the other one. So plus 1.28 times 10 to the 9th times 12. Plus 2.56 times 10 to the 7th. Or wait, 1, 2, 3, 4, 5, 6. No, it would be times 10 to the 8th. Is that right? Because like 1, 2, 3, 4, 5, 6, 7, 8. So is that correct? Because like here, 1, 2, 3, 4, 5, 6, 7, 8, 9. So yeah, I guess it is just off by 1. I was thinking it was off by 2 places, but no. So that looks right. And that divided by 2 gigahertz So since we're doing it the long way today, the rigorous way, we are going to, oh yeah, now we need the internet, don't we? Is it, okay, so here it loaded and we see it was 1 through 8 that we did. So I think the internet is working right on time. So we're gonna do show me gigahertz on Wikipedia. So gigahertz is 10 to the 9th hertz. So we say 2 times 10 to the 9th Now let's just type this into, like, we could use Google. 2.56 times 10 to the 9th times 1 plus 1.28 times 10 to the 9th times 12 plus 2.56 times 10 to the 8th times, oh, I didn't finish it on my on Milton. It's times 5. So I'm being very generous with, or very conservative, I guess, with my use of parentheses here. I'm really trying to make sure it does the order of operations right. I don't think I need all these parentheses, but it doesn't hurt. So might as well put them in. I am assuming that power will happen before multiplication, though. So that gives me 9.6 seconds. .6 seconds. Now what we're saying is for two processors, so dual core, we're splitting the workload up across threads, and I don't understand why the branch instructions are the same across cores. I guess the idea is, you imagine if you have a function and you parallelize it, so you're running the same function in different threads, but each one is computing, just a sub part of the workload, like what you do in things like CUDA or OpenGL, and things like that. So if you do that, the control flow is the same across functions, right? But the arithmetic and load store is less per thread because it's only doing a sub part of the problem. So that's why the branch instructions would be the same number of branch instructions, I guess. But still, though, if you imagine it in like a loop, if you imagine a loop, you'd say the branch instructions is the number of branch instructions inside the loop, which I guess includes the loop itself, uh, times the number of iterations, right? But if you're splitting the workload across threads, then the number of iterations per thread is going to be like whatever the work size is of that thread, whatever the workload of that worker thread is. So like if we say we have, 4 threads, and say we have 2 branch instructions in a loop, and we're going to loop 100 times, right? Just single threaded. And you split that workload up across 4 threads, then each thread is going to loop 25 times. So I would intuitively, I would think that you would be doing the 256 million branch instructions divided by p, more or less, right? But my understanding of the question is that it's 256 million per thread, because it says assume on a single processor the program uses 256 million branch instructions. Assume that as the program is parallelized to run over multiple cores, the number of branch instructions per processor remains the same. Hello, Croifa. I gave you a shout out in the last book club episode. I'm doing a book club episode right now, continuation of the last one. We're working through the exercises in Computer Organization and Design, Chapter 1. So, like, if I understand the question correctly here, it's telling me that we're supposed to assume 256 million branch instructions per processor. Which doesn't make sense to me, but we're going to roll with it because that's what the question is asking, I guess. So, so we're saying if we're splitting this up across 2 cores, then I guess we just stick the division in there for the arithmetic and load store instructions, right? So I think what you could do, and I'm not 100% confident about this, that this is correct, but like we're saying this is the number of instructions, right? So if I say that number divided by 0.7 times 2 threads, and then we do the same to this one here, divide by times 2 threads. And then because these are the branch instructions, we're supposed to leave that part of it alone, according to the question, if I understand it correctly. So if we do that, we get 7.04 seconds for 2 cores. And then we go on to 4 cores. So again, we just bump the core count up. So this is another thing for me to think about, actually. So I want to see how many characters this is, because this is a really long computation that we're doing, and I'm thinking about for my own pcalc program. I have a limit on the size of an input, so I just want to see how big this is. Oh, it's only 81 characters, so a really long expression is definitely within range. Right now I have it set to 255 max, but I have it like configurable. But the thing is, with like XEB, with X11, to do text rendering over X11, like you can only send like a byte worth at a time, like 256 characters at a time, which is why I set the limit to 255 in my program. You could handle that, of course, by rendering in multiple passes, but if 256 characters is going to be enough for like all the computation I do, then there's no reason to make it higher. And I thought this is a good example of a really long expression, and that's very much in range. So I feel good about that. So 3.84 for 4. And then for 8, $2.24. So if we normalize all those against one core, this would be 1, and then we do 7.04 divided by, and I'm just going to do this on my phone calculator because we might need that expression again. I could just open another tab, but I have my phone right here, so might as well use that. So 7.04 divided by 9.6. So that's going to be 0.73. And then 3.84 divided by 9.6. 1.4, 2.24 divided by 9.6 is 0.23. So those are the normalized times comparatively. Croifa says, I try to bypass X11 as much as possible. I pretty much just get an OpenGL context with GLX and then to direct rendering. Yeah, I considered that for my calculator program. I thought about doing a Vulkan backend rather than OpenGL, but I just feel like doing direct rendering is overkill for a little calculator program. Like I would definitely do that if I was rendering something more complex, but I pretty much just need text, some rectangles and lines, and some color. That's all I really need to render for a calculator. So I figured it would be a lot simpler to just use X11 for rendering. So that's what I'm doing in my calculator program. But I designed it so that it's very easy to add multiple backends. I structured it like how Milton is and how handmade-hero is, that kind of structure of the program. So I did an XCB backend, and right now what I'm doing is I'm writing a new backend that's pure X11. So it just like communicates with Unix sockets directly talking the protocol instead of using a library. And the big advantage of that is that I use, like to use XCB, it gives you back things that you need to free. So you need to rely on the standard library as well, and like the C runtime and all that if you're going to use XCB. So if I'm just talking the X11 protocol directly, I can strip out the XCB library, which means I can also get rid of the C standard library and the C runtime. And I expect my program is going to be really small when I get rid of all that. I'm not relying on anything from the C standard library, so it'll be straightforward to do that once I've finished porting everything over. And I think that's going to be really cool. But that's still a work in progress. I posted on Twitter, I don't know if you saw this, right here. I stumbled onto a real gem today, low-level graphics on Linux. So I found this thing that talks about how you do this. It goes over the Linux frame buffer device, direct rendering manager, and the X11 direct connection, which is what I'm doing. And one cool thing about this is it's very similar to just using XCB. And the thing about X11, the way it's designed to be able to use TCP as well as Unix sockets, like originally it was designed back in the old days to be used over TCP. You can actually apparently set it up so that you use TCP to connect to X11, and then you use a packet sniffer. Like you literally just use a packet sniffer to see what the protocol is sending over TCP. And I haven't done that yet, but that seems like a really cool way to figure out what libraries are doing rather than just reading source code of libraries. With an X11 program, you can actually sniff packets over TCP to do that. So I'm probably going to be trying that at some point as well. But yeah, this is a really, really cool little article here. I definitely recommend checking that out if you're interested in that kind of thing. Anyway, back to what we were doing. So in terms of relative speedups, this is like if you normalize against it, you're basically saying the percent faster, right? This only took 73% of the time that one core did. 8 cores only took, like 23% of the time. I think that's how you would interpret that. That's how I'm going to say, that's my answer as far as comparing them relatively to each other. So I think we finished 1.9.1, find the total execution time for 1, 2, 4, and 8 processors and show the relative speed up. So, like I say, those are my answers. I might be wrong, but and again, I'll shout out. I have a thread on the forums. COAD 1.13 exercises. So here we can discuss my answers and answers you guys get if you follow along with this. And obviously the videos aren't public yet, but when they are, this will be a good resource for the community to discuss these episodes. So let's move on to 1.9.2. If the CPI of the arithmetic instructions was doubled, what would the impact be on the execution time of the program on 1, 2, 4, or 8 processors? So arithmetic was the one that has a CPI of 1. So it's a good thing I left that equation open in Google, because now I can just change the CPI and we'll see the answer. So let me see here. The CPI is this times 1, so we're going to double it. So there's a CPI of 2. This is going to be the answer for 8 cores. So for 8 cores, we get 2.46. So let me make a new table here. So I'm just going to put the time right next to it. So this one was 2.48, I think. 2.46. Let's round it to 2.47. Now let's do 4 cores. Uh, 4.297, so let's round it to 4.30. And again, we're comparing to these values right here. And for two cores, uh, 6.58. So is that right? No. I still have this one set to 8. I think I did something wrong in my previous computations. So let me redo these. Okay. So for 8, it's going to be like this, 2.46. That's what we have. For 4, this needs to change to 4. As does this. 4.29, 4.30, that's what I have. For 2 cores, this needs to change to 2. So does this one. 7.95. I was going to say, we shouldn't be saying it shouldn't be faster if you're increasing the CPI. So 7.95. All right. Next we have a single core. Or wait, for a single core, it wouldn't be times 0.7. So let me just take out the 0.7 here. So 10.88. Do I find it important to do the math out by hand? I'd be really tempted to just use a spreadsheet. Yes, I do find it important to do the math out by hand for a few reasons. First of all, just because I'm old school and I prefer paper over doing spreadsheets and things like that. I just like working things out on paper. And besides that, I think doing things like this on paper, the long way and the hard way, I think it ingrains it in your mind better. I think it's more like useful for learning. It'll stick in your mind better this way. At least to me. I don't know if that's true for everybody. But I find it helpful. But maybe that's just because, like, this is how I grew up, learning in school. When we work out like math problems in elementary school or something, you're doing your math homework, you don't just go and type it in a spreadsheet. At least I didn't. We learn to work things out on paper. And so, going through school, you do a hell of a lot of that. And so it's just so ingrained in my, my upbringing that that's how I prefer to do things. So 10.88. All right, now, so it says, if the CPI of the arithmetic instructions was doubled, what would the impact be? So what I have here is what the impact would be. To what should the CPI of load store instructions be reduced in order for a single processor to match the performance of 4 processors using the original CPI values? Okay. So there's 2 ways to do this, arithmetic and trial and error. It's tempting to just do trial and error because I have the expression right here to play with. But if we're using the original CPI values, this value right here needs to be 1. And there's the 9.6 that we see here. So we're saying if we want it to be equal to 3.84, how much do I need to lower this value right here? So let's just do a little trial and error here. So at a CPI of 2, it's 3.2. It's exactly 3.84 at a CPI of 3. So the answer should be 3, but we're also going to do the algebra. So if you have this expression here, and we replace the 12, here, let me use the eraser. So we replace the 12 with an n, and that's what we're solving for, and then we say equals 3.84. So first of all, you can say times 10 or times 2 times 10 to the 9th. And that gets rid of the denominator. And then if we say minus 2.56 times 10 to the 9th times 1. And then we also need to subtract the 2.56 times 10 to the 8th. And then we just have 1.28 times 10 to the 9th times n is equal to the stuff on the right here. So then if we divide by 1.28 times 10 to the 9th, we'd get n. So you take all this stuff divided by 1.28 times 10 to the 9th. And if I did my math correctly, we should get the same answer. So let me type this into my phone calculator here. So 3.84 times 2 times 10. And where's the power on this thing? There it is. Okay, and then we take that minus 2.56 times 10 to the 9th. And that's going to be times 1. Minus 2.56 times 10 to the 8th. And then we need to wrap all that in parentheses. Divided by 1.28 times 10 to the 9th. I got 3.8 doing my algebra, but here I got here I got 3 exactly. So 2.56 times 10 to the 9th, the divide by 1 does nothing, times 1, plus 1.28 times 10 to the 9th, divided by 1 times 3. This one's times 5. Dividing by the 2 times 10 to the 9th. Okay, so at least I'm not alone in my algebra giving me 3.8. So what did we do wrong? We're trying to find here, for context, I don't know how long you've been following along insofar as, but for context, we're we're solving, if we set the CPI of the load store instructions, which is the n in this equation here, if we set that to something, yeah, so let me explain what we're doing. So 2.56 times 10 to the ninth, that's the number of instructions for arithmetic, and there's a CPI of 1, okay? And then 1.28 times 10 to the ninth, that's the number of instructions for load and stores, times 10 to the ninth, or 1.28 times 10 to the ninth, that's the number of instructions. And then the n here is the CPI, and originally it was 12, okay? And then 2.56 times 10 to the 8th, that's the number of branch instructions. And that has a CPI of 5. I didn't write... Oh, that's why I made a mistake. Because I never wrote the times 5 here. This right here is times 5. And I put that in when I did it in Google, but I forgot to write it. And that's what just screwed us up here. So the idea is you have those many those instructions for those different types of instructions with those specific CPIs, and we computed the time for different numbers of cores, where it said that for when you're splitting it across cores, assume that it's the number of instructions divided by 0.7 times p, where p is the number of processors or cores or threads, or however you want to think of it. But for branch instructions, it said it's going to be the same. So I thought intuitively it should be, the branch instructions should be 2.56 times 10 to the 8th divided by p. But they're saying it should be the same. So I'm assuming that reading the question literally, they mean keep it at 2.56 or 256 million instructions per thread for branches. So I worked through the math, and we got these times for the different number of processors, right? And for 4, we got 3.84. So now it's saying for a single processor, a single threaded program, a single core, we want to change the CPI of load and store instructions so that you get the performance of 4 cores from the original. So that was saying, so what we're saying is we want to change the CPI to get 3.84 seconds as the time for running this program. And so it should be 3 according to my Google calculations, and that should be right because what we had written down was wrong. I forgot the times 5 here. So if I stick the times 5 in at the appropriate place, that'd be right there. Now let me do that calculation again on my phone, and we'll see what we get. So this should be times 5, and yeah, that gives us 3 exactly. So on my phone, we got 3. So yeah, I believe the answer is 3, assuming I didn't make mistakes elsewhere. I might be interpreting the question wrong, I don't know, but based on all the priors, the answer should be 3. Okay, so that was 1.9.3, 1.9.3. Okay, so going on, we have 1.10. Assume a 15 centimeter diameter wafer has a cost of 12, contains 84 dies, and has 0.02 defects per centimeter squared. Assume a 20 centimeter diameter wafer has a cost of 15, contains 100 dies, and has 0.031 defects per centimeter squared. And then the sub-questions to this are find the yield for both wafers, find the cost per die for both wafers. If the number of dies per wafer is increased by 10% and the defects per area unit increases by 15%, find the die area and yield. And then finally, assume a fabrication process improves the yield from 0.92 to 0.95. Find the defects per area unit for each version of the technology given a die area of 200 millimeters squared. So let's write down what we know, first of all. So we have a 15 centimeter diameter wafer. So it says the cost is 12. There's no unit on that. It's just 12 something. 12 rupees, right? So 12 space bucks. 84 dies. And 0.020 defects per centimeter squared. And the 15 centimeter, that's diameter. All right, and then we have a 20 centimeter diameter wafer. It has a cost of 15, so we're going to say 15 space bucks. Contains 100 dies. And has 0.031 defects per centimeter squared. And the first question is find the yield for both wafers. So did I write down equations for this? I have a feeling I didn't, but maybe I did. So yield, do we have anything along those lines in here? Chip manufacturing costs. Okay, cost per die is equal to cost per wafer divided by dies per wafer times yield. Dies per wafer is equal to wafer area divided by die area. Yield is equal to 1 over 1 plus defects per area times die area over 2 squared. And our question is find the yield for both wafers. So we should just be able to plug it into that equation there and get the answer. Let me double check the equation, make sure I didn't write it down wrong. So let's find the chapter on chip manufacturing. Where was the chip manufacturing? Okay, here's a picture of a die. That must be the right place. Or, I mean, a picture of a wafer. Now, where were those equations? Here we go. So yeah, yield is equal to 1 plus defects per area times die area over 2, and then all that squared. So it looks like I wrote everything down correctly. insofar as asks, are these exercises available online? I don't believe they are. I've heard from people that you can find the ARM version of the book somewhere. I don't know legally or not, but you might be able to find a PDF of the book somewhere. In terms of the official publisher website, we did look to see if we can get the answers to the exercises, and it looks like you need to be like actually with an institution of some kind. Like you need to be an actual like university professor teaching a course with this book to get the exercises, or the exercise answers, I mean. Maybe you can get like a teacher's edition of the book or something, but I imagine there's red tape around like buying a teacher's edition. I don't know. So, yeah, I don't think the official website has the exercises as far as I know. If someone finds them online, let us know. And like I say, we have this forum topic, so that would be a good place to post it if someone does find them. But otherwise, you could buy a copy of the book. I know textbooks are very expensive though, so I wouldn't blame you if you didn't. Speaking of which, I would like to do a giveaway type of thing at some point. I'm at like, I think I'm at around 95 subscribers on YouTube, and my goal for a really long time has been to hit 100. And we're pretty close to that. So one thing I want to do when we hit 100 subscribers is do a giveaway, and maybe have like the winner gets their choice of either computer organization and design risc-v edition or a high five 1, something like that. So I do want to do a giveaway, but I'm not gonna like actually officially announce a giveaway until we hit the 100 subscriber mark. But maybe people listening to this, maybe that might give some people the incentive to subscribe. But Carafa says, might be worth contacting the publisher. They might just give you some stuff, as it might be good PR for them. Well, there's two sides to that coin, because and I was talking to risc-v about this. Technically, it's a violation of like copyright law to be reading their book like without permission from the authors or the publisher. So like, it's a pretty gray area, because this is the kind of thing that people who do like let's plays on YouTube run into, where the game is not, they don't have like copyright over that, but they're playing it. And in my eyes, what I do on the book club is the same thing as a let's play. It's just a let's read. Right? I'm just like breaking new ground in that it's a different kind of medium, but it's the same kind of idea, right? And so I do feel that what I do is good publicity for them. I know people have bought copies of the book because of me, but they might not look at it the same way. They might not be very happy that I'm doing this. So I'd rather not contact the publisher. Like we'll just see if we ever end up getting a cease and desist or something. Maybe they'd be supportive of it and see it the way we see it. But for now, I'd rather just, do my own thing and hope that I don't get a cease and desist letter. So for that reason, I'm not gonna contact the publisher over this. But it would be very cool if we could get some stuff. But like I say, I'd rather just leave it alone. But yeah, anyway, let's copy the yield equation. over to where we were doing our stuff. So yield is 1 over 1 plus defects per area times die area over 2 squared. Cruyff says, interesting. I think that if you are only using like 10% or something like that of the original work, then it is considered fair use, but I'm not a lawyer. Yeah, I'm not a lawyer either, and I have no idea. But we're planning to read through the entire book. I think that would qualify as being using over 10% of the original. Obviously, we're adding a lot to it in that I'm, adding my own thoughts to it. I'm working through exercises and check yourselves and things like that, showing, what I get, what my thought process is, discussing it with you guys on the chat. It's a community thing. There is a lot of value added over just, the original book with what I'm doing. A lot of original stuff to what I'm doing. But by and large, we're piggybacking off of their work. So, they could definitely look at it from that side and go after it legally if they were so inclined. I'm pretty sure they'd potentially be in the right there. And my view on the copyright side of it is I feel like this kind of content should totally be legal. I think it's totally a good thing that we're doing here. And, laws don't always coincide with, like, what's morally right, so to speak. Richard Stallman says that kind of thing in terms of talking about piracy. He considers that sharing things to be a very, like, morally good thing to do. And he sees, like, copyright laws that restrict that as being, not morally sound. And I have the same view on piracy, too, just as an aside. But I'm kind of in the same ground on this, in that I feel what we're doing is a morally good thing. And you shouldn't necessarily, go on what the laws say. So that's kind of my philosophy on that. I know that's a pretty big tangent, but it was an interesting little discussion there. Insofar as says, RMS said it was better to steal bread than write proprietary software. Yeah, I would not be surprised if he said that. That definitely sounds like him. So let's get back to the problem now. So let me see here. So here we are. Okay. So yield, let's see if I can remember this. 1 over 1 plus die area over 2 squared. Something like that. So let me just double check that. Where was yield? Oh, defects per area times die area. I thought I was missing something. Defects. What is it, per area? Here, let me just look it up in the book again, so I can reference that while I copy it down. 1 plus defects per area times die area over 2. and then all of that squared. Crayf says, I'm not sure I agree that piracy is a good thing, but we can save that discussion for another time. Don't want to hijack the stream. Yeah, definitely. It would be fun to have maybe like a side stream where we just like debate that or something. Oh yeah, it would be awesome if you talked about it on your stream as well. But yeah, that's a little too off topic for this stream. So, and I just as a little aside to that, I want to say I don't think piracy, like as a whole, is necessarily like totally good. But I think I think it's a lot more like a gray area with some aspects of it that are good and some aspects of it that are bad. That's kind of where I stand on it. Just to get that out there. But I definitely lean towards the Richard Stallman side of things in terms of that. But anyway, so we need to find the yield for the two wafers here. So here's the information we've got. The diameter of the wafer, the cost, the number of dies, the number of defects per centimeter squared. So that would be this part of it right here, defects per area. But then we need to figure out the die area. So I guess they don't straight up give us the die area, do they? But we know how many dies there are, and we know the diameter of the wafer. So maybe we can figure it out based on that. So let's think about this. So, I mean, if we know the diameter of the wafer, let me draw a really bad circle here. So there's our wafer. The perimeter of it is a little messy, but you get the idea. Now the diameter is going to be this. So, I mean, the way they run dies out, like the edges get cut off, but then it's like only the full dies that count towards the die total. So I mean, if we know the area of the wafer and we know how many dies it's supposed to produce, we should be able to figure out the size of the dies. But it's like, I need to think about the math for that. It's not super clear to me. So, I mean, first of all, I guess we should figure out the total area of the wafer. So, how do you get area from diameter? Isn't it like pi r squared or something? Area of circle. Yeah, the area is pi r squared. So we have the diameter. So if we take half the diameter squared times pi, that would give us the area. I wonder if Google can do pi. It probably can't. Let's say pi times, what was the diameter? This one's 15 centimeters. So we're going to say times 15 over 2. Square that. Okay, so it apparently does do pi. It says it's 176.71 centimeters squared would be the area of the wafer. So, I mean, if we want to divide that up into 84 pieces, 84 dies, I guess you can maybe roughly say divide that number by 84, but that doesn't really account for the edges of the wafer, which, I mean, those don't get counted towards the die count, but they're part of this area. So that kind of complicates things. So I don't know if it would be correct to just take this number and divide it by 84 to get the die area per, like the die area. And I mean, I wonder, it kind of depends on how you grid it too, doesn't it? Like how you decide to lay it out. I mean, obviously there'd be like an optimal way to lay the grid out to get the most complete wafers out of it. Yeah, in the picture I have here, the picture in the book of a wafer, they're rectangular wafers. They're 20.7 by 10.5 millimeters for an i7. But I think we're talking about square dies here. Because it doesn't tell us the dimensions of a die in this question. The question is, assume a 15 centimeter diameter wafer has a cost of 12, contains 84 dies, and has 0.02 defects per centimeter squared. Assume a 20 centimeter diameter wafer has a cost of 15, contains 100 dies, and has 0.031 defects per centimeter squared. That's all it tells us. So we don't know whether the dies are rectangular or square. All we know... Oh no, the wafers are circular. The wafers are circles. But the dies are either squares or rectangles, and they they pattern the parts that get cut off on the outer part of the circle. Like those parts still get patterned, but they don't create a complete die. It's just easier. The process is easier that way to like pattern it, even though it gets cut off. But only the complete ones make a die. So out of the ones that are complete, like the complete rectangles or circles, or I mean rectangles or squares that fit into this circle, there's 84 of them. So we're trying to pack, the problem right that we're solving right here is we're trying to pack 84 complete either squares or rectangles. It doesn't really matter, I guess, what the shape of the die is. The point is we have 84 of them, and we need to pack them into this circle, which is 15 centimeters across. And then once we have that, we can figure out what the die size is based on, like, because the die size needs to be something, all the dies are the same size. So, we figure out what size it needs to be to pack 84 of them in there. That's kind of the idea here. So algebraically, I still don't see exactly how you go about solving that. I mean, I know this would be the area for the first wafer in centimeters squared. And I know we have 84 dies. So like I say, a really rough approximation would be to take the 176 point blah 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 and divide it by 84, right? Because that would divide it into 84 like squares basically. So I guess if you do that and then just chop off the decimal at the end and consider that to be the slop on the edge of the circles, maybe that would be the, like, actually correct. I'm not totally sure. But I'm gonna roll with that because I don't see a better way to do it. So if we divide this by 84, so let's say the dies are 2 centimeters squared. Right, so if we say 2 centimeters squared times 84, so that gives us 336 centimeters. Or would that be centimeters squared? I think that would just give us centimeters because it's 176.7 square centimeters for the circle. So like if we just say 2 times 84, 168 square centimeters total is what the 84 is taking up. And then 176.71, like that number minus the number I just showed you would be the slop on the around the perimeter of the circle that doesn't complete, like doesn't make a full die. So I'm gonna go with saying there's 2 centimeters squared for die area. So what we're saying is the yield would be 1 over 1 plus 0.02 times, and then 2 squared over 2, that's just going to be 2. And then this needs to be squared. So let me, I guess we don't need that long equation in Google anymore, do we? Okay, so 1 divided by, and it's going to be 1 plus 0.02, I think it was. Yeah, 0.02 times 2, and then all of that squared. So I predicted the yield to be 0.92. So like 92% of the wafer is good, I guess is what that means. Like it makes 92% makes working dies. So for this one, I'm going to say 0.924. So let's just call it 0.92. And then we want to do the other one. So this one is 20 centimeters. And it makes, I can't tell if what I wrote there was supposed to be like a 9 or a 1. 100. It's supposed to be a 1. So let me make that a little clearer. Okay, so now we need to do 20 centimeters is the diameter. So pi times 20 divided by 2, and then we want to square that. So that gives us pi shifted a few decimal places, right? Because the 20 divided by 2 gives you 10, and then squared times pi. So, okay, now we want to take that divided by 100 dies. So that's just going to give you pi again, isn't it? I'm pretty sure that's just going to give us pi. Yeah. So that gives us pi. So the die area for this one is pi. If I'm doing the math correctly. So then the yield would be 1 over 1 plus, let's see, what were the defects for this one? 0.03 times pi over 2 squared. So if we say 1 over 1 plus pi over 2, I guess I don't need to put that in parentheses. Or wait. 1 plus 0.03 times. So that doesn't need parentheses. And then that just needs to be squared. So 0.91. So those are my answers for the first part of this problem. Next, we need to find the cost per die for both wafers. So isn't that just going to be the cost of the wafer divided by the number of dies? Or the number of dies times the yield? Yeah, exactly. Cost per die is cost per wafer divided by dies per wafer times yield. So just what, exactly what I thought intuitively. So if we have 12 space bucks divided by 84 times 0.92. 12 divided by 84 times 0.92. So that gives me 0.155. So like the cost per die of the first one is going to be 15 space cents, basically, or 16, I guess, rounding up. Or would you round up? Would you round down in a situation like this when you're working with money? I'm just going to round it up to 16. We're going to say 16 space cents. All right. And now we're doing 15 space bucks divided by 100 dies times 0.91 defect our yield. So that one's going to be 0.1648. So I mean, let's just call it 16 space cents again. So those are my answers for cost of the dies. And then it says, if the number of dies per wafer is increased by 10% and the defects per area unit increases by 15%, find the die area and yield. Okay. So first of all, we need to increase the dies per wafer by 10% for each of them. So the new dies per wafer is going to be 84 times 1.1. So 92.4, but you can't have 0.4 of a wafer, so 92 would be the first one. And then 100 times 1.1 would just be 110. So new dies per wafer, and I'm going to call these like A and B. And then we increase the defects as well by 15%. So the first one was 0.02. So 0.02 times 1.15, it was 15%, right? So that is going to give us, and then here I'll say defects. So this one's going to be 0.023, and this one is going to be 0.03 times 1.15. So this one's going to be 0.0345. So let's just say 0.035, I guess. I don't know how many like decimals of precision we need. So I'm just going to say 0.035 for defects. Yeah, that's the precision we want, because this one was, they gave it in 0.020. So they gave us 3 decimal places, so we should only give 3 decimal places, right? So, okay, so we want to calculate the new dies per area, right? The die area and the yield, the new die area and yield, okay. So let's make another table here. A, B, die area, yield, okay, so we'll need the die area before we can calculate the yield. So let's focus on those. So to get the die area, I was taking the area of the wafer divided by the number of dies per wafer. So we know the new number of dies per wafer. So it's going to be the same area, but I didn't leave that open in a tab. So we're going to need to recalculate the area for each. So let's do the first one. It's 15 centimeters diameter. So that's going to be pi times 15 over 2 squared. So that's 176.71 centimeters squared. And then we're going to take that divided by the 92 dies. So that gives us 1.92 centimeters squared per die. So let's say that one's 1.92. And then the next one Or wait a minute. That's including the slop though. So would I say see, when I did this before, like this one I just chopped off the decimal and said it was 2. This one I didn't bother doing it. I didn't account for slop and I just said pi. So that's not necessarily right, is it? And chopping off the decimal point might not be right either. So yeah, I'm still grappling with how we should best deal with the slop. Because like if this one's 1.92, so like here, let me leave this number open in the tab. And then we're saying 1.92 times, what was it, like 92? Of course, that's using the assumption from the previous one, isn't it? Or no, the die area doesn't depend on the previous calculations, does it? So that gives us 176.64. But is that saying we could actually fit, like that's not saying we could actually fit that many squares though in it, right? Like we want to know how many proper dies we can fit. But again, doesn't that kind of depend on whether it's a rectangle or a square? Like depending on the shape, I think that would affect how many you can fit. Maybe not though. Hmm. Yeah, I'm really confused about this because do we have like a formula for giving us die area based on wafer diameter? Oh wait, we have dies per wafer, wafer area, die area here. So this equation we could solve for die area, right? Dies per wafer equals wafer area divided by die area. So dies per wafer times die area is equal to wafer area, which means wafer area divided by dies per wafer is equal to die area. So we are supposed to just use wafer area divided by dies per wafer. based on that, I'm pretty confident now that we are supposed to just use the wafer area divided by dice per wafer, which means that one of my answers is wrong. But this is right, the 1.92. And the pi one would be right because I used pi and I forgot to try to account for the slop. Turns out the algebra works out that I guess you don't need to account for the slop or something. Like, because we already know the number of dies, I guess the math works out. I don't know. It would probably, like, if you visualized it, if you drew like a circle in GIMP or something and then fit rectangles into it, you'd probably see how it works out better. But I'm not going to bother spending all that time doing that. So I'm just going to trust the algebra that I just did. And we need to rework through this one right here, the original first wafer. So it would be the 176 number, this number, divided by 84, 2.10. So this should be a 2.1. Let me just do that in Google Calculator quick. So 1 over 1 plus 0.02 times 2.1, and then we need to square all that stuff on the bottom. So the yield still comes out to be 0.92. It's 0.92101 blah blah blah. So 0.92 is the yield. And then we also calculated the cost. So where was the equation for that? Cost per die. Or that's just the intuitive cost per wafer divided by dies per wafer times yield. So that's going to give us the same answer because the yield did not significantly change. Like the insignificant decimal places changed, but I don't think those decimal places are significant enough. So I think it's still 16 cents per die. You know, they didn't give us a unit on cost, but like I'm just saying, like if the 12 is 12 bucks, then 16 cents in like US currency. So now we need to do the die area for B. And that one, we're saying there's 110 dies, and we need the, okay, 20 centimeter diameter. So this changes to a 20. And then divide that by the, or not 101, 110. So that gives us 2.855, so let's say 2.86. 2.86. And now we need the yield for each of those. So going back to the equations here, the yield is 1 over 1 plus defects times die area, and then squared, everything on the bottom squared. So the defects are 0.023 for the first one. So 0.023. And then that's going to be times die area over 2. So wait a minute. When we say die area over 2, so I was thinking we were canceling out, but no, it would be the 1.92. So maybe I did do the yield wrong still for the previous ones. I'll double check in a sec. So 1.92 divided by 2. And then all of this is going to be squared. So I get a 0.957, so let's call it 0.96 yield. I take that to mean 96% yield. And for the next one, it's going to be 0.035. And this number is going to be 2.86. And my phone calculator is telling me that that would give 0.906. So let's call it 0.91, or 91% yield. And let me redo the ones from before. Okay, so did I not write down the die area? I think or the die area was the 2.1. So that should actually be 2.1 divided by 2. So let me see here. First of all, this value needs to be 0.02. This value needs to be 2.1. Okay, so the actual yield for the first one should have been 0.959. So we're going to call it 0.96. And so that's going to change the cost as well, isn't it? We'll need to recalculate that. The yield for the second one is going to be, let's see, this needs to change to 0.031. This needs to change to, let me see here, pi. So I put pi over 2 in the thing, but was the yeah, that's right. It is supposed to be pi over 2. So I think I did the second one right. It is supposed to be 0.91 yield. So let's redo the cost per die for the first one yet again. So we know the cost per wafer is 12, and we're going to say 12 divided by 84 times 0.96. So that gives me 0.207 blah blah blah. So it should be 21 cents. And again, I'm making up the unit here because they didn't give us a unit. Okay, and I think I got the new ones correct, right? I'm not going to double check. We're just going to say those are my answers. Okay, what's next? Assume a fabrication process improves the yield from 0.92 to 0.95. So wait a minute, they just gave us the yield. 0.92. I said 0.96 for the first one, 0.91 for the second one. So the question says assume a fabrication process improves the yield from 0.92 to 0.95. Find the defects per area unit for each version of the technology given a die area of 200 millimeters squared. So I don't know what to make of that. The fact that it says improves the yield from 0.92 to 0.95, like they could be talking about the yield of the second one because we calculated that to be 0.91. So like maybe they just rounded it differently. Or they could be talking about not like a separate problem, but it's written as a subproblem, which makes me think they're referencing the previous stuff. So that confuses me, but so they want us to find defects per area, and let's pretend that this is like separate from the previous questions and just go with what it tells us. So the new yield is 0.95. The defects per area unit is what we're trying to find, and the die area is 200 millimeters squared. So we know the yield, we know the die area, so we can just solve it in a bubble. It doesn't depend on the previous questions. So 0.95 equals 1 over 1 plus something times, what was the die area? The die area is 200 millimeters squared. And it says find the defects per area unit for each version. They're talking about the one that has the yield of 0.92 and the one that has the yield of 0.95. Okay, so this question is just in a bubble. It's not related to the last ones, which is really confusing because they made it as a sub question within this one. Like this is 1.10, and we did 1.10.1, 1.10.2, 1.10.3, and the question we're on now is 1.10.4. But it's like a separate question, not depending on the previous ones. So that's really, I think, poorly done on their part. in the structure of the questions there. That made me think my answers were wrong on the previous one, which they might be, I don't know, but so let's see here. So it said the original was 0.92, so we say 0.92 equals 1 over 1 plus n times, and the die area is supposed to be 200 millimeters squared. So we're going to say 200 divided by 2 and then all this needs to be squared. So first of all, 200 divided by 2, that's just going to give you 100, right? So 0.92 equals 1 over 1 plus n times 100, all that squared. And we're trying to solve for n. So 0.92 times 1 plus n times 100 squared should equal 1. So let's just say divide by 0.92. So 1 plus n times 100 squared equals 1 over 0.92. And then if we take the square root of both sides, we get 1 plus n times 100 is equal to the square root of 1 over 0.92. And then so like the order of operations is like this, right? So we would say this minus 1 and then divided by 100. So that should give us n. So we're saying, let's see, square roots 1 over 0.92 and that minus 1 and then divide by 100. So did I do that right? Because I get 0.000425 blah blah blah. Or wait, yeah, because we're talking in millimeters when before we were talking in centimeters. That's the reason the decimal places are different. Right, if I convert 200 millimeters squared to centimeters squared, here, I don't trust Google for this. I'm going to go to Wolfram Alpha. Right, so it's 2 centimeters squared. So if I say 2 divided by 2, that's 1. So this just simplifies to 1, or to n, I mean. So it's 1 plus n squared. So we don't need to divide by 100 is the short story there. So I calculate 0.04 defects per area in terms of centimeters, which is reasonable. Like that lines up with the values we were seeing before. So the next one is when it's equal to 0.95. So we should be able to do the same exact calculation and just change this to 0.95. And then we get 0.0259. So let's just call it 0.026. So those are my answers for problem 10. When did I start streaming? I might want to call it here. So I think I am going to call it here, and we will continue later. I'll probably do another stream, another book club stream tonight. We still have a number of problems to go through. But yeah, I'm going to call it here for now. So thank you everyone who tuned in today. And thank you everyone who watches on the YouTube archive, which is available at risky.tv. And you can follow me on Twitter to get updates about the series at HMN_risky. Thank you also to everyone who supports me on Patreon. If you would like to financially support my series, you can do so at patreon.risky.tv. I will see you in the next episode, and stay risky, everyone.